Hello, and welcome to the Inverses Day 1 video. Please make sure that you've read the Canvas page on Inverses Day 1 so that you can see all of the kind of overarching notes about inverses. We will be covering them in this video as well as in class, but having that going into this video is going to be very helpful. So we're going to be skipping around in our blank notes. We're going to be starting with problem number 1. It says, in each problem, find the inverse. Oh, I forgot this was still a lightsaber. Find the inverse of a function, then graph both the function and its inverse. So for problems 1 and 2, we're just going to do problem 1. They are, in fact, ordered pairs. Now, whenever we think of the word inverses, sometimes we might think of the word reverse or switch or opposite. So that's exactly what we are going to do. We are going to take our x and y values and switch them. So switch x and y values. This is how we are going to find our inverse. So if we take our original function f of x, which we are going to do, in green, I'm going to pause this video, graph those points, and then restart it. So here we have all of our points for f of x graphed. Feel free to pause this video and take a moment and do this yourself as well. But these are all of our graphed points. Now what we're going to do for our inverse, which I believe, you know what? I think I'm going to do that in red. So in red, we're going to have our f inverse, and I'm just going to take all the points and switch their x and y values. So this first point of 2, 4 becomes 4, 2. Negative 5, 3 becomes 3, negative 5, and so on and so forth. So I'm just going to take all of my points, switch their x and y's. When we get to 1, 1, and negative 4, when we switch the x and y values, they're the same, and that's okay. Negative 2, negative 1, and negative 1, 3. So all of these points here are our f inverse of x. So that is saying that we have all of our x and y values switched or flipped at this point. So again, I'm going to pause and graph all these points. So here you can see that I've graphed all the points. Again, feel free to pause the video if you'd like to plot these, or please pause the video to plot these. We can see that some of these are overlapping. I'm going to change this just to a laser pointer. Some of these are overlapping, so I've just kind of circled them within themselves. But something else that was noted about inverse functions, particularly when looking at the graph, is that we may notice that they are reflected over the line y is equal to x. So if we were to plot that line, I'm just going to do that with a dashed line right here. So 1, 1, 2, 2, 3, 3, so on and so forth. We can see that our green dots and our red dots are mirrored or reflected over this line of y is equal to x. So in all of our past videos, we have spent time looking at how to find operations or compositions in tables or ordered pairs, in graphs, as well as with functions. So this was kind of, I know we graphed here, but this was kind of more of an example with ordered pairs. Next, I'm going to scoot down a ways, and we're going to take a look at how we would do this with a graph and a little bit with equation as well. So we're actually going to skip down to problem number 4. Right here, where we're given n of x is equal to x squared, and it wants me to find n inverse of x. So the way we're going to do this with our equation is there are first 4 steps, and you can see these on the Canvas page if you'd like to write them down. But the first step is to replace f of x with y. In this case, it's n of x, just whatever your function is, replace that with y. Your next step is you're going to switch your x and y values. Next, you're going to solve for y, or try to get y by itself. You're going to solve for y. And then lastly, you're going to replace y with f inverse of x, or in this case, n inverse of x. So I'm going to take you through how we might use these steps to solve to find an inverse function. So in this case, if we are starting with n of x is equal to x squared, our first step is going to replace, in this case, n of x with y. Next step is we are going to switch our x and our y values so that we have x is equal to y squared. And then third step is to solve for y. So the reason we want to solve for y, we start by switching x and y and then solving for y, is because we're essentially undoing all of the steps or going in reverse order from what the original function is asking us to do. So in this step, when we are solving for y, we are going to square root both sides, and we are going to get the positive and negative version of the square root of x. Remember, whenever you're taking the square root of something, you must put the plus and minus in front of that. And we officially have y by itself. So the very last step is more of a notational piece. We're going to replace y with f inverse of x, or in this case, n inverse of x is equal to the positive and negative version of the square root of x. So that's kind of the steps that we can take in order to find inverses with equations. But if we're going to do it with graphs, for instance, if we just did this with a graph, I might take a look here at this n of x is equal to x squared, and I make a table out of that. So we'll do an x and y table. Again, this is for x squared. Let's use the points -2, -1, 0, 1, and 2. If I square each of these, so let's see, -2 squared is 4, -1 squared is 1, I got 0, 1, and then 4. So if I was to plot all these points, I'm going to do them kind of quick, and I'm also going to add the points 3, 9, and -3, 9, just to make sure that we're graphing from one end of the graph to the other. Please make sure you're always going to the edges of your graph. Now, when we did this with our ordered pairs, we switched our x and y's and the coordinates. When we did it with the equation, step 2 was switching the x and y. So here, when we're dealing with the graph or with these tables, we're going to switch the x and y values and create a new table for our inverse, which in this case is positive and negative version of the square root of x. So we're just going to take our x and y values, and we're going to switch them. So now our x values are 4, 1, 0, 1, and 4, and the y values are -2, -1, 0, 1, and 2. So when we graph those points, some of them are going to overlap, and that's okay. I'm going to look something, and I am doing those, flipping those extra points as well. You don't necessarily have to, just making sure that you're graphing from one end to the other. And this is our, let me get my highlighter, there we go. This is our inverse function here. So again, just a reminder, I'll put this off to the side. Oop, that's still the highlighter, my bad. We want to we call these tables t-tables. So make a t-table, then switch your x and y values. And again, just like the points that we have, both of these functions are reflected over the line y is equal to x. So if we were to graph that line, it would look something like this. So we can see that if we took the green graph and we reflected it over the blue line, it's going to give us the red graph. This question right here, we're not going to cover right now, but just what do you notice? It could be some of the things we've been writing in yellow. It could just be what you notice overall. Are things functions? Are things not? Let me know. But let's just do one more practice with graph before we talk about one-to-one functions. So we're taking a look. We're going to move to problem 7. It says, draw the inverse of each graph. Hint, make a t-table, find the inverse, graph the new points. That's exactly, oh, I can't slide. There we go. That's exactly what we did up here. So we're just going to do the same thing now. So if we took a look at this line right here, we can find all of the nice points. So we can do those here. You can name just a few, you can name all of them, but please make sure that you're switching or you're graphing from one end of the graph to the other. So if I was to make a table for this one, for my green one, I looked at these points. Okay, I have -1, 6, got 0, 4, 1, 2, 2, 0, and 3, -2. Well, to find the inverse, I've made my t-table. I'm going to find the inverse of the t-table, or switch the x and the y values, and get 6, -1, 4, 0, 2, 1, 0, 2, and -2, 3. So it's going to look something like this. Oops, sorry, that's on the wrong spot. There we go. I'm actually going to just keep going just in case you use some of the other points. And remember, we're going to graph this from one end. Ooh, that's very uneven. There we go. We're going to graph this from one end to the other. So we can now see, here's our inverse. Even though we didn't come up with the equation, this is what you can always do for a graph. Now, the question is, when we're graphing, sometimes we'll notice things are functions, sometimes they're not. Well, our next question is, how do we know if something is a one-to-one function? So again, if you take a look at that Canvas page, you'll see some notes on one-to-one functions. But essentially, a one-to-one function, I'll move this up just a little bit, there we go. A one-to-one function, it means that the original problem and the inverse are both functions. So it means that the original problem and the inverse are both functions, so one-to-one. If you remember the definition of a function, it's that every x value has exactly one y value. Well, this also means for one-to-one that every y value has exactly one x value. And the way that we test that is we use the vertical line test and the horizontal line test. So it must pass both the vertical and horizontal line test. So we use, let's see, where's my highlighter? There we go. We use the vertical line test when dealing with the original problem. We've practiced that quite a bit. But we're going to use the horizontal line test to figure out if the inverse is a function. However, I will say that, oops, that's still the highlighter, that the test, the vertical and horizontal line tests, the tests are checked with the original problem. So you don't have to actually graph the inverse and then do the vertical and horizontal line test. You can do that with the original. So for us, that's always the green. If we were to take, I don't really have a horizontal lightsaber, so I'm just going to use my laser pointer. So for this, just the green line, if we were to do a horizontal line test here, that's a function, or probably vertical line test. Now if we do the horizontal line test, that's also a function. So this means that problem 7 is one-to-one. Where if we were to go back and take a look at problem number 4, just looking at our green graph, if we ran a vertical line up and down, it's a function, we're all good. But if we did a horizontal line test, oh no, that doesn't pass the horizontal line test. It hits it at 2 points, which means that problem 4 is not a one-to-one function. So that's how we would go through and check there. We'll address problem 9 tomorrow in class. But that's kind of how we would take a look briefly at tables, at graphs, as well as equations. Now, the equations part gets a little bit tricky, so I want to make sure we get some extra practice with that. So if we move down here we have 6 problems where it just says find the inverse of each function symbolically or using algebra. It's really just using those 4 steps. So feel free to kind of rewind and take a look at those 4 steps again, or take a look at the Canvas page. We're going to be doing problems A, B, and D. I'm going to zoom in a little bit for that just so that we have the space. So for problem A, again, first step, we're going to replace f of x with y. Second step, we're going to switch our x and our y values. So we have x is equal to 3y minus 1. Then we're going to solve to get y by itself. So we're going to add 1 to both sides. We're going to divide both sides by 3. And then lastly, we're going to replace y with f inverse of x. Now, when I write this equation, if I was then to ask you to graph this, x plus 1 over 3 doesn't really help. So I'm going to write this in mx plus b form, or slope-intercept form. So I'm going to write this as 1/3 x plus 1/3 as my final answer. Let's try it again. So if we take a look at problem B, again, replace f of x with y. Switch your x and y values. We have x is equal to 2y squared plus 8. I'm going to subtract 8 on both sides. And then from here, I'm going to divide both sides by 2. So we have x minus 8 over 2 is equal to y squared, or you can think of that as 1/2 x minus 4, where I'm dividing each of those pieces by 4, is equal to y squared. And then to get y by itself, I'm going to square root both sides. So we're going to have the positive and negative version of the square root of 1/2 x minus 4 is equal to y. And then lastly, we are going to replace y with f inverse of x, and so that we have our inverse function. Let's try that once more. When we take a look at problem D, whenever we're dealing with rational functions or fractions, I think things get a little bit more challenging, more exciting. So we're still going to keep the same steps in there. I'm going to replace f of x with y, and then we're going to switch our x and our y values. So we have x is equal to 1 over 3y minus 2. And now we have to solve to get y by itself. So let's see, I look at this and I go, not sure what to do. Y's in the denominator of something, and I want to get the y out, but we can't get the y out by itself. So in order to get rid of this fraction or this division, I'm going to use multiplication. And I'm going to multiply both sides by the entire denominator of 3y minus 2. So we end up with x times 3y minus 2 is equal to 1. Now from here, you can distribute the x if you want, or you can also divide both sides by x. Both will get you correct answers. I think I'm actually going to distribute the x in this case, so that we have 3xy minus 2x is equal to 1. From here, I'm going to add 2x to both sides. So we have 1 plus 2x. And then we have 3, remember this is 3 times x times y. So in order to do this multiplication, we have to divide. So I'm not just going to divide by 3. I'm not going to just divide by x. I'm going to divide by 3x on both sides, so that we get y is equal to 1 plus 2x over 3x. Now, this is as simplified as we can get. We cannot get any farther than this because of that 1 plus in the numerator. So I ran out of space. For our last step, we're going to replace y with f inverse of x. So I'll have f inverse of x is equal to 1 plus 2x over 3x. And there we have it. So that's finding inverses with ordered pairs or tables. as well as graphs and equations. Before we finish this video, it's going to go a little bit longer. Down here we do have some questions really quick, just reminding you about domain, looking at those restrictions, and reminding ourselves when do we maybe not have any restrictions. So if we look at A, D, and E, if I take a look at E, I say, you know what? I'm not allowed to divide by 0, so that denominator, x minus 7, cannot be equal to 0, or we know that x cannot be 7, because if we were to plug 7 into this equation, we would be dividing by 0. So our domain would be from negative infinity all the way up to 7, really, really close to 7, but not quite equal to, and then we can continue from 7 onward. So that would be one of our restrictions. Another example of restrictions is in D, where we cannot take the square root of a negative number. So we have to say, hey, 5 minus x, that has to be greater than or equal to 0. So I know that this can be 0 because square root of 0 is fine, and it can be any positive number, but it can't be negative. So here, if we were to solve, I'm actually going to add x to both sides. So we have 5 is greater than or equal to x, which means x can be any number less than 5. It can be 4, it can be 3, it could be negative 20. So when I write up my domain, we get as low as we can, which in this case is negative infinity, and we go as high as we can, which is to 5, with a bracket because we have that or equal to. Now, if we take a look at A, at negative 2x plus 6, I don't see anywhere where we could possibly dividing by 0, and I don't see anywhere with a square root. So if that's the case, then our domain is just negative infinity to positive infinity, and this is a case with no restrictions. So I wanted to throw this in as a little bit of review. I know this video was kind of long. Thank you for sticking with us. Let me know if you have any questions, and I look forward to seeing you tomorrow.